So I'm Michael Bell, and this is Physics Lab 5, the falling slinky. So for our introduction, the purpose of the lab was to analyze a video of a falling slinky and predict its motion. To do this, we use Tracker, which is the software that we use to track the observed position of the slinky. And then we also use GlowScript, which is a computational model, and we use it to predict and graph the ideal motion of the slinky. So our goal of this lab was to determine the bottom of the slinky, or determine the physics behind the fact that the bottom of the slinky stays stationary in the model compared to the video. And our result was, although there are some slight fluctuations, the bottom of the slinky remains stationary throughout the whole video. So our fundamental principles were Newton's second law, which is system's change in momentum is proportional to the net force applied, and that can be shown by F net equals change of P over change of T. We also use drag force, which is a resistance force that is caused by the motion of the body through a fluid like air. Most fluids like water, air, any other fluid has a resistance force applied, so we use that. And then our gravitational swinging force, which is the same force and the tension, and it's opposite to gravitational force. So for our assumptions, we kept the mass. We assumed the mass was 0.218 kilograms with a drag height of 1.75 meters, and the initial position was negative 1.632 times 10 to the negative third, comma 2.72 times 10 to the negative fourth, comma 0 meters, because it was basically 2 day for us. And then our initial velocity was 0.000 meters per second. And this is the picture we use for our estimations. So this is a few initial conditions we kept in our GlowScript model: the ball mass of 0.218, and then the vector of 0, and then negative 1.6, and 2.7, and then negative 4, and then comma 0. We just did this to keep it all constant throughout the experiment. Our delta was 0.01, and then our g-force or gravity was 9.8, which we kept constant. And then drag was proportionally constant, which was 75, and we assumed that because of our model and to keep it all constant throughout the experiment. So here's more of our computational model. We used, as long as the time was less than 8.1333, because we kept that constant because of the video we had, and so we had to just make sure it was less than that because we didn't have the actual physics behind keep it larger. So our W is calculating the force behind the model. It was our potential force. We have our FD, which is the another gravitational force, but the air resistance we felt, and we use the normal the magnitude of the velocity times 2 times the normal vector of the ball velocity, and then we use that to calculate the whole drag force, which is F net equals W plus FD. So then we use the position update and velocity update to calculate iteratively through our times. So for our results, we had one positive source of error, which is the motion observed experienced slightly variation due to the external forces that are not accounted for in the model, like potentially there was a gravitational force that we did not account for, and maybe an added motion that we did not account for in terms of releasing the spring and mass system. But there was also a source of error, which is the possible source of inaccurate point mass tracking in the tracker video analysis. So, in all, why does the bottom of the motion slinky stay stationary? This is because the net force in the y direction is 0 because the forces cancel each other out. As long as the tension in the force of the slinky is equal to the magnitude and opposite in direction of the gravitational force, this whole system stays stationary. The magnitude of the force is 0 in terms of the bottom slinking area. Slinky. And the second question is, would the bottom of the slinky remain stationary if a large weight was attached to the bottom? And our answer was, if the slinky were sufficiently long and had a sufficiently large spring constant, it would remain stationary. But however, because there was motion, it was not stationary.